to the last general interest seminar of the academic year 11-12. We're definitely going out with a bang with this one. Many of you are from the School of Physics and Astronomy, but we do have a lot of guests from out with the school and also from out with the university, so you're very welcome indeed. And our general interest seminars are open lectures, so if you would like to attend more, you can follow us on our website. I have huge pleasure in welcoming Jim Al-Khalili to the school to give our last GI lecture of the year. I'm very grateful to him to say thank you to the invitation. Jim, as I'm sure many of you know, all of you know probably, is Professor of Theoretical Physics and Chair of Public Engagement in Science at the University of Surrey. I could go on for a very, very long time about his achievements, but I'm merely going to refer you to Wikipedia on this occasion. He is an expert on mathematical models of atomic nuclei. He supports Leeds United, but we can forgive him for that. And of course, he's known as him off the telly. But I would also point out he's also him off the radio, and I very much recommend the radio programs. So thank you very much, Jim. Take it away.
Well, thank you very much, Karen. Yes, good afternoon, everyone. So this is one of two talks I'm giving up in Edinburgh today. I'm giving another talk to the Royal Society of Edinburgh later this afternoon on Alan Turing, which is something I know less about than the subject you'll be glad to hear, subject of this afternoon's lecture here. So this is a talk based on the book, which wasn't quite based on the TV series. A few years ago I made a BBC 4 three-part series called Science and Islam, which for me was background research for the book. And the book Pathfinders was really my foray into history of science, and actually devoting some considerable amount of my time and efforts into researching history of science for about a year and a half. You know, I didn't do much research in nuclear physics because I was reading through various sort of manuscripts and going down to sort of as far as I could do primary sources on this fascinating subject. So I want to focus in the lecture today more about physics than the other sciences that where they were developed and where there were contributions from this period in history. The book Pathfinders originally was going to be called The House of Wisdom. The House of Wisdom is that almost mythical academy that is believed to have existed in medieval Baghdad during sort of the first, second century of Islam, in particular at the beginning of the 9th century. I say mythical because there are no archaeological remains of this academy. It's thought to have been a centre very much like the Library of Alexandria hundreds of years earlier, 1,000 years earlier, where it became a focal point drawing many scholars from all walks of learning to translate text, to write text, and to sort of think deep thoughts and come up with original ideas. So The House of Wisdom was this great title for the book until Penguin, the publishers, realised there was another book in America on the same subject with the same title, House of Wisdom. Now, initially, they said, fine, let's let the other author and publishers worry about the fact there are two books of the same title. They were quite bullish and said, you know, yours will be far bigger seller. And at the last minute they got cold feet and they decided to change the title, and they suggested Pathfinders. Now Pathfinders, as far as I and the publishers could tell, was from a quote attributed to a medieval or sort of Middle Ages scholar from North Africa called Ibn Khaldun. Now Ibn Khaldun is regarded as almost the father of economic theory, the father of social science, very, very influential and influenced many European writers. We couldn't find the quote though. And then it turned out that in fact, so the quote was this: "He who finds a new path is a pathfinder, even if the trail has to be found again by others. And he who walks far ahead of his contemporaries is a leader, even though centuries passed before he's recognized as such." It turns out that that was a quote by an author, Nathaniel Schmidt, who wrote a book about the biography of Ibn Khaldun. So he's referring to Ibn Khaldun. But in fact, this name Pathfinder really, I think, fits very well as a title, because it depicts the contributions of so many of these great scholars and scientists, many of whom are unknown in the West. And my thesis, my argument is that they really should be far better known than they are. Many of us in the West will have heard of a few of them, and I'll mention a few names, but certainly people like Avicenna and Averroes, great medieval philosophers who influenced European thinking, especially in the way they sort of merged Greek philosophy with monotheistic theology, ideas, you know, Aristotle's ideas merging with Islam, Judaism and Christianity. So these people were known. But I want to tell the story about other great scholars who achieved a lot in science that we don't hear about. We learn in the West about the ancient Greeks and how clever they were, undoubtedly so. And names that there are still household names today: Aristotle, Archimedes, Plato, Ptolemy, Euclid. And then we assume, because Western Europe fell into the Dark Ages with the fall of Rome, that the rest of the world was also in the Dark Ages, and that nothing happened of note until Copernicus and Vesalius and the Renaissance in Europe. But science doesn't work that way. Science doesn't rise and fall the way civilizations rise and fall. Science is a continuum. You stand on the shoulders of giants. You build on what's come before. And it's a baton that's passed on from one culture, one civilization to the next. And so the story here is of that gap in science between ancient Greece and the European Renaissance. And more importantly, a period which was much more than simply a holding bay for Greek ideas translated from Greek into Arabic until Europe awakened again, ready to receive those ideas back again, translated from Arabic back to Latin. This was a period where many important advances were made, and I'll just give you an example of a few of them. It's centered around Baghdad. Now, Baghdad was the capital of a new empire called the Abbasid Empire, the Abbasid dynasty. They were very much influenced by Persian culture. The capital before Baghdad was in Damascus, but they wanted to build this new city, which was part of what used to be the Persian Empire in present-day Iraq. And the site of Baghdad was where they were already, this was, you know, where the two great rivers, the Tigris and Euphrates, come very close together. So it was a very fertile part of Mesopotamia. It was also a place where there were lots of villages and market towns and so on. So they built the round city of Baghdad in 762. And this is a lovely sort of historian of science map of the round city with various names of different regions and districts there. What's more interesting is to superimpose that on modern Baghdad. You see an area slightly smaller than the US-controlled Green Zone, which I suspect is now just the US Embassy in Baghdad. I think it's the largest embassy in the world. But this leads me to my motivation for being interested in this subject. Because, as many of you may already know, but certainly from my surname, I was born in Baghdad. My father's from Iraq, my mother's English. And so I was born in Baghdad and grew up and spent my childhood there. So it's only now, when I sort of reach middle age, that I suddenly feel I have this, I don't know, a pull to try and dig up my cultural heritage. And I say cultural rather than spiritual, because I'm not religious. You know, my father's an agnostic Muslim. My mother's a very devout, born-again Christian. They've never had an argument about religion, as far as I can tell. but it's almost inevitably, especially going to something like theoretical physics, it's probably inevitable. I was going to fall between the stools somewhere. But so my interest, so in a sense I say that because I want to get across this very important point that this is not special pleading. I'm not telling you how wonderful this was because Islam as a religion is wonderful and enlightened. I'm not interested in being positive or negative about Islam, but simply to put it into historical context. Certainly without the Islamic Empire, this wouldn't have happened, and that's what I want to go into. Okay, well, the Abbasid dynasty were very obsessed with culture, they were obsessed with scholarship, they ruled at a time when the Islamic Empire was at its greatest in terms of power and extent. The most famous caliph was Harun al-Rashid. He's a character who appears regularly in 1001 Nights. The caliph Harun al-Rashid is always walking around Baghdad with his trusty vizier Jafar, and he's entered sort of mythology. But he was the ruler during the golden age of Baghdad, and we see this wonderful 19th century painting of King Charlemagne visiting Harun al-Rashid in Baghdad. King Charlemagne was his counterpart, the powerhouse, the powerful king in Europe at around the beginning of the 9th century. And the historians write that King Charlemagne was in awe of the opulence and glamour of Baghdad. Baghdad was then the center of the civilized world. That was where things were happening. That was the place to be. Not just scientists, scholars, but musicians, poets, historians, all walks of life. Baghdad was the center of that sort of, the ancient, the medieval world. It was regarded, some historians dispute this, but it is regarded possibly as the first city with a population of over 1 million. Some historians will debate whether there were cities in China around that time that had reached 1 million. But it was certainly larger than any of the great centers in Europe. Athens, Rome, Constantinople. And it had superseded them as being the center. So it was very opulent, and it was awash with money. And a lot of that money was used as patronage for science and scholarship and learning. Very similar to the way the European Renaissance grew out of Florence in Italy in the Middle Ages. Again, it was the wealthy Medici family who would sponsor the artists and sculptors of Florence, and it was from there that the whole Renaissance movement really began and spread across Italy and then across Europe. So again, it's money helps encourage and pay for people to be able to think these deep thoughts. But it was Harun al-Rashid's son, another caliph by the name of al-Ma'mun, who is thought to have built this academy, this house of wisdom, the Bayt al-Hikmah. Some historians would say it was nothing more than a translation house or a library, and after all, we can't be sure exactly how big it was. We're not sure where it was because there are no archaeological remains of it. What we do know is that it holds this hugely important symbolic power as a center where scholars were gravitating to from all across the empire and beyond. It was certainly a time of great tolerance towards other religions. The very best physicians in Baghdad were Christians. Some of the very best mathematicians who made real advances were Jewish mathematicians working in Baghdad. There seems to be not much of an issue, other than, I think, if you didn't convert to Islam, you had to pay higher taxes. But other than that, okay. Other than that, it was a time when there was a freedom of thinking. And for original science, you need freedom of expression, freedom of thought, away from constraints of religion, in a way that many countries in the Muslim world today don't have, and strive to have, but don't have. It's all very well, and it's a good first sign that wealthy Gulf states are pouring money into producing new universities, KAUST is the first university in Saudi Arabia that has men and women working studying alongside each other. There are other Gulf states that are building new laboratories and attracting offshoots of American universities to do research there. But you need more than that. You need this freedom of expression to be able to think, come up with original ideas without any constraints. And that's certainly what seems to have happened in Baghdad at this time. I want to go through then a few of the, I'll pick up a few examples of where progress was made. The obvious thing, when people say, oh, the Arabs, medieval Arabs, oh yes, they gave us the number system that we use. Well, of course, that comes from India. And it's known as Indian numerals, Hindu numerals, or very often Hindu-Arabic numerals. And you can see the way, sort of this cursive, symbolic way of writing the decimal system in this case, although obviously decimals didn't arrive later, develops into the decimal symbols that we use today. Certainly until the decimal system was brought across from India first to the Islamic world and then later to Europe, other ways of writing numbers were much more common. So using letters as numbers, that's how the Greeks, what Greeks did, many who wrote in Arabic also did, like Roman numerals. And it took a long time even for mathematicians to appreciate how advantageous it is to use the decimal system. Try multiplying two Roman numerals together. There are tricks, there are ways of doing it, there are techniques, right? But it's probably best to save Roman numerals for page numbering and nothing much more than that today. But the other thing I want to mention is the zero. Because again, if people don't know much about it, say, oh yeah, what did the Arabs give us? Oh, zero. Well, actually, they didn't give us zero, and that leads me just to a quick aside as to why I refer to this as Arabic science. Had I not mentioned what I'm going to mention, I'm sure it will come up in a question at the end. But let me say it now. You may think it will be more obvious to refer to this period in history of science as the golden age of Islamic science. I'm not alone in not wanting to use that phrase. Historians of science around the world don't use that phrase, because I want to imagine what would you think when I talk about Christian science? It means something very different, right? We don't want to even go there. Or more seriously, Jewish science, which was a derogatory term used by the Nazis in the 1930s to denigrate the work of people like Einstein, suggesting that somehow Einstein's work was of lower quality than good Aryan physics, Aryan science. So, one should take care not to label the science, the period of a particular era in a particular civilization, by the religion of those who practice that science. In any case, as I mentioned, many of these scientists were not Muslims. There were Christians, Jews, Zoroastrians, Sabians, agnostics, coming from all different walks and cultures. You may worry that if I call it Arabic science, that I'm neglecting the rather important fact that actually, if I were to list the top 20 greatest, like you'll do sort of in an autistic male scientist sort of way, top 10 this, top 10, what's your dream team, top 10 films, top 10 Greek scientists, and you put them on. I'd have Aristotle and Archimedes in midfield. I'd probably I'd have Hipparchus in goal. He seems like a safe pair of hands. So if I were to list the same, I could do the same thing with these scientists in this era, and actually more than half of them will not be Arabs. They'd be Persians. And by Persia, I mean not just modern-day Iran, but the whole of Central Asia. So, am I somehow missing, crediting these people by calling it Arabic science? The point is this. The point is I'm not referring to it as Arab science. Arabic refers to the language, and it refers to the language of the Islamic Empire. It was the language of the Quran. And so everyone in the empire, whether it was their mother tongue or not, learned Arabic in order to read the Quran. And it turned out this was then becoming the official language of the empire. It meant that all texts were written in Arabic. So Arabic science refers to that period when Arabic was the language of science. You can quibble. We can say, well, is modern day science English science? And that is what historians now regard as the most appropriate way of labeling it. Okay, 0. Who invented 0? Well, it depends on what we mean, because you can say, well, who came up with a symbol for 0? Who came up with the concept of 0, of nothingness? Who came up with 0 as a number? The symbol 0 has its origins in ancient Babylon. Same part of the world, by the way. In modern day Iraq. The Babylonians used a symbol as a placeholder for 0 around about a century before the Mayans did in Central America. But all they were doing was using it as a placeholder, in decimals, to tell the difference between 11 and 101. You had to put a symbol in there to say this is a gap. But beyond that, they didn't really have much of a notion of 0. Around about the same time, around about 300 BC, Aristotle wrote about 0 as a concept, as a notion, nothingness, emptiness, the void. But he didn't use it in a mathematical sense. It was the Indians who developed the idea of 0 as a number, halfway between +1 and -1, that you can do arithmetic and calculations with, and that it was useful. And so that was sort of exported as a package with the decimals to the Islamic world in around about the 8th, 9th century. I do refer to these numbers, the decimal system, as Hindu Arabic numerals. Well, if the decimal system came from India, then what did Arabic science have to offer to allow it, to credit it with a name on like having a name on a publication on a paper? What have you done to credit it beyond just maybe an acknowledgement at the end? Okay, so this is a page from a book from the 10th century by a mathematician who worked in Baghdad by the name of al-Khalili, which translates as the Euclidean, because his job was to translate and comment on Euclid's great text on geometry, the elements. But it's also, this is interesting, because this page in particular is interesting, because it's the example of the first use of the decimal point, the decimal place. Zooming in. There, left to right, 179685. That dash over the 9, see the 9 is very similar to the way we would write it, suggests that what that number is, and we know that from the rest of the text, that he's writing down 179.685. In this text, which is the first example of using decimal point, he was trying to get across the idea that actually using decimals can, in many cases, be much more convenient than to use fractions, because until then, anything less than 1 was written as a fraction. What he was doing, in fact, was doing a particular example and showing how useful this was. So this is what he was doing. He was say, take a number and add to it its 10th, right? And then take that number and add to it that 10th, and so on, 3 times. So essentially, it's the number multiplied by the cube of 11 tenths. He was suggesting that if you wanted to work this out, in fact, what he was doing, his number that he took was x is 135, quite randomly. But he was making the point that if you substitute 135 into there, it's rather awkward to use fractions. And he was suggesting that decimals were a more convenient way of going. Now, it may well be that round about this time, in parallel, and completely separately, mathematicians in China were also developing decimal points. We don't know as much about science and mathematics in medieval China, and in any case, I guess that isn't my story. Okay, but so for me, the decimal point is part of the whole decimal system, and this is the contribution from the Islamic world. Another area of mathematics This is a book by a Persian mathematician by the name of Al-Khwarizmi. And it is the first book on algebra. This man, Al-Khwarizmi, is regarded as the father of algebra. The word algebra comes from the title of this book, Al-Jabr, which means completion. The book of completion, Kitab al-Jabr, was a book on how to solve algebraic equations. He didn't get too complicated, and he was solving quadratic equations, but essentially a lot of the book was all about doing examples and how you'd use algebra to help in working out taxes and inheritance and dividing up land and so on in agriculture. But some people may say, well, that wasn't the first time people were using algebra. We now know that the ancient Babylonians could solve quadratic equations. There are clay tablets with cuneiform writing on, showing the formula. Essentially, x is minus b plus minus square root of b squared minus 4ac over 2a. And you know, that's the way you work out the solution of a quadratic equation. Certainly, there were Greeks who were doing what we might think is algebra, Diophantus. And in fact, there's a whole family of equations that are named after him, which I'll say something about in a moment. But this was the first book which really did algebra the way we do it now. It's the first book that treated the unknown, the x, as a real thing in itself, that you manipulate and move around. It wasn't just a symbol hiding behind it a specific answer, a specific number. That's what the Babylonians were doing. They would only provide a recipe for working something out for a particular problem, particular equation. This was a general solution for quadratic equations. This was something that was really what we would define today as algebra. What's really fascinating is that this book was written, it's a textbook, a maths textbook on algebra, without a single equation in it. It was written entirely in prose. You say, you take the unknown, you multiply it by itself, then you add to it 3 times the unknown, and the answer is 10. Here is how you work out what the unknown is. And then he'd go through explaining what we could do in 2 or 3 lines. But actually it was a book that was then accessible and available for many people beyond the scholars and mathematicians to be able to use and follow. Okay, so symbolic algebra was something that happened much later in Europe. And in a sense, that's just a way of a shorthand way of doing things. That's a way of being able to do algebra much more neatly and efficiently. It's not necessary in order to do algebra. Okay, so here's an example of what the Babylonians would have done. As I say, a specific problem. They say, a typical problem would be find a number, if when you add it to its reciprocal, it leads to this number, some known being here, for instance. I mean, obviously they didn't write it like that. And of course, that's an example of a quadratic equation, which we can sort of manipulate to something that is more familiar to us from school days. But they didn't develop general algebraic rules. They would solve specific problems. What Al-Khwarizmi did was provide the recipe, provide the algorithm. And where does algorithm come from? The Latinized version of Al-Khwarizmi's name, algorithmus. I kid you not. I don't make this stuff up. So it's quite nice. His great text gives us the word algebra, and his name gives us the word algorithm, which is the basis of I guess, of computer science. Okay. I want to just make the distinction between what I call algebra and number theory. So Diophantus, this Greek who I said was doing what we might think is algebra. He wasn't really doing algebra. He was doing what we call number theory. And so what we now call Diophantian equations was something that he wrote about. Indian scholars like Brahmagupta would also study particular types of Diophantian equations, something called the Pell equation, which are more difficult than quadratic equations. as you can see here, there are two unknowns. A is some number, okay, for a particular problem. But there are two unknowns, x and y. So this one equation, two unknowns, doesn't have a unique solution. Okay, there are lots of x's for which there are also, paired up with lots of y's that would give that, make that equation correct. Brahmagupta, by the way, posed a challenge to mathematicians in India. Say, can you find the solution? What is the smallest value of x and y for which this equation is correct if A is 92? And he suggested anyone who can solve the problem within a year earn the right to be called a mathematician. Okay, well, today it's very easy. We have computers and it's not so difficult to just allow your computer to chunk through, leap through x's and y's. Okay, so that's something about mathematics. I want to talk about a scholar for a few minutes who is not as well known as some we may have heard of in Europe. So I mentioned at the beginning, we've heard of Avicenna. His Persian name, or indeed his Arabic name, is Ibn Sina. And he was the great superstar of the age. So we're talking about the end of the 10th and the beginning of the 11th century. A contemporary of his is another Persian by the name of Biruni. Biruni, in a sense, I would argue, was the greater scientist. He was the sharper, more analytical thinker. I don't want to draw comparisons, but if you know something about the history of science, back in the 1920s, there was a long-running debate between Niels Bohr and Einstein about the meaning of quantum mechanics. And they were to and fro, and it came to a head in a famous conference in 1927 in Belgium, the Solvay conference, where Einstein was trying to pick holes in Niels Bohr's formulation, well, not in the mathematics, but in his interpretation of quantum mechanics, and then Bohr would come back to him. Well, 1,000 years earlier, these two guys, Ibn Sina and Biruni, had similar discussions about physics. And it's wonderful, although they were talking about medieval scientists, Biruni would write to Ibn Sina and say, so why does ice float? And Ibn Sina would say, well, I thought about this, and that's because ice has tiny pores in it, tiny holes, and makes it less dense. And Biruni would say, no, I don't think that's true. I don't find that can't be right. And then how does the sun rays, how do we feel the heat of the sun? Does the heat travel through from the sun to the earth, or does it suddenly, does the sun's light do something? Questions which were deep, meaningful questions in physics, where the scientists at the time didn't quite have the tools or the knowledge to be able to answer them completely. Biruni, as I've written there, I regard him as the Da Vinci of the medieval world, because he was much more than a scientist. He was a historian, he was an astronomer, he was a mathematician, he was a geographer. Just any faculty in a modern university you care to think of, he probably had something to say about that subject, and helped advance the rudimentary ideas there. He helped lay the foundations of trigonometry, for instance. He wrote a book on the history of the ancient world, the kings and caliphs and rulers of the ancient world, as was known at the time. He wrote a book on the geography and geology of the Indian subcontinent. He travelled widely in what's today India and Pakistan. What he's most famous for, and which is really neat, actually, is what I want to tell you about now. He measured the circumference of the Earth far more accurately than anyone had done before. Until then, the way the ancient Greeks measured the circumference of the Earth, because this idea that it's only until Christopher Columbus that we realised the Earth wasn't flat is nonsense. The ancient Greeks knew the Earth was round. You could just tell that by looking at ships coming up over the horizon in the sea to know that it was curved. So they'd worked out a way, and the way that the Greeks would do it is to do with the angle of inclination of the sun. They'd measure the angle, and then they'd count paces until that angle changed by 1 degree. It's actually not, it's a clever idea, right? And knowing that, 1 degree, there's 360 degrees in a circle, the distance they travelled, they multiply that by 360. And they could get pretty close. Biruni writes in his text when he talks about his idea, he says it's far more sensible than to be going around counting paces in the desert. You know, that's a completely useless way of doing things. And in particular, the Greeks had a way of measuring, they'd measure the distance from Alexandria to Aswan in Egypt. And they said, well, and so you can measure the distance, and then you measure the angle, the inclination of the sun during the equinox, the same day of the year, both in Alexandria and Aswan, and the difference in angle, you multiply that by 360 divided by that, multiplied by the distance between Alexandria and Aswan. Anyway, the fact is, they could never measure that distance accurately. And there are lots of reasons why they could have gone wrong. So Biruni wanted a more rigorous way of working out the size of the Earth. So he first measures the height of a mountain. And essentially what he does is he has this device, a square with graded, ruled sides, you know, distances, and he has, so DG is like, there's a moving rod, and he can move it up so that he aligns it with the top of the mountain. And then he just uses geometry. The idea of similar triangles, where, you know, there's certain triangles, small triangles that he knows two sides of because he's measured them on his instrument, and you know, he would have to know something about the larger triangle. And there are a couple of steps. I talk about this in my book, and so I warn people, if you're not into geometry, you can skip, you know, the next page. But if you are, you're keeping me honest by, you know, going through the steps. But essentially, it's like in the way modern sort of architects will measure using theodolites. You know, they will measure heights of buildings and so on, and distances from angles. So he can measure the height of the mountain EF. He needed to find the right mountain because the mountain not only had to have this flat plane in order to measure its height, he also had to be able to see the horizon from the mountain. And he found a mountain over a large flat plain in central Pakistan. He then has to climb to the top of the mountain and measure the angle of inclination to the horizon from the horizontal. So that angle phi, I've obviously overemphasized it because that's a very high mountain. But this is just, you know, so you wouldn't see much if I didn't exaggerate. Okay? The angle phi, in fact, is around about ½ a degree. And he uses a very accurate astrolabe, a device for measuring, used in astronomy at the time, for measuring angles very, very accurately. And he can get to fractions, you know, minutes and fractions of a minute of arc using that device. So if he knows the angle phi from top of the mountain, he knows the height of the mountain h, he can just construct the cosine of phi. And of course, because, you know, from rudimentary geometry, we know that phi there is equivalent to the angle phi, making that right angled triangle. The circle is the Earth, big R is the radius of the Earth. So he's got an equation there where big R is the only unknown, and he can manipulate it to work out the radius. He then multiplies that by twice pi, he gets the circumference of the Earth, and he got it to within 1% of the accurate answer, so just under 25,000 miles. Now, of course, the circumference of the Earth varies depending on whether we're measuring around the equator or around the poles, and also there is some issue about, you know, he doesn't put error bars, for instance, in his calculation, so we don't know how accurate. And so, for me, it's not so much that he got to within 1%. For me, it's the ingenuity of the method that he used. Okay, since I mentioned cosine, a nice, fun diversion is just something I didn't know until I sort of did the research of the book. Where does the word sine come from? S-I-N-E. Okay, so you may think you know, maybe you do know, sorry, but for those who don't, it begins with Indian mathematicians. Okay, it arrived into Europe via an Englishman by the name of Robert of Chester in the 12th century, and he gave us that word. Okay, but the fact is, it had a rather novel root from the Hindus. So, in Sanskrit, the language that was written in India at the time, they used the word ja'arda, which means half the bowstring. So you can imagine a circle here, and the chord and the arc make a bow, and if the circle has unit radius of 1, in whatever units you can, then half the bowstring is that vertical side of the right angle triangle. Now, sine of angle A is that length, half the bowstring, divided by the radius, which is 1. Okay, so sine A is that length. So ja'arda is what the Hindus would call the sine of an angle. It's half the chord of a circle of unit radius. They abbreviated that to jiva in a lot of their writing. Now, in the Islamic world, along with all the Greek texts that they got hold of and they translated, they also translated the Hindu mathematical texts, and jiva was translated into Arabic as jiba. There is no letter V in the Arabic language. Okay? So v just becomes b, jiba. And even today, the Arabic for sign is jabe. Okay? Because in Arabic, very often you don't write the vowels as full letters. So it was just the equivalent of a J and a B, j, b. So it wasn't obvious that you pronounce it jiba. So if you just see a J and a B, you'd say jib or jabe is how they pronounce it. Now, jabe was translated into Latin by Robert of Chester. And jabe in Arabic means pocket. Now, it's not meant to be pronounced jabe, it was jiba, but it's because of you've thrown the vowels out, it became pronounced as jabe. He thought it was meant as pocket, and the Latin for pocket is sinus. So Paul Robert of Chester, we credit him with giving us the word sign. He's gone to the, this is a guy who travelled very extensively in the Islamic world to get Arabic texts and translate them into Latin. And etymologically, he's gone slightly astray, but we're not going to hold him to account for that. Okay, I want to give enough time for questions, so I'll whiz through what I've got left in the next 5 or 10 minutes at most. So I want to say something about greatest physicists, and if you think about the greatest physicists of the ancient Greeks, there's no doubt it was Archimedes. He was the first experimental scientist, really. I mean, he was carrying out experiments. He, in all sense of the word, he was what we would today call a physicist. The greatest physicist of all time, Isaac Newton, who was the greatest physicist in the span of 2,000 years between them. Guess what? I'm going to say it's one of my Arab mates. Ibn al-Haytham is another one of these great unsung heroes in the history of science. He was hugely influential in Europe in the Middle Ages. A lot of his work was translated into Latin. But along with so many of these other scientists, once your Galileos and Keplers and Newtons come along, and Europe just explodes with the scientific revolution and just zooms off exponentially in terms of advances, you forget some of these earlier names. So let me say something about Ibn Haytham. He's a wonderfully colourful character. Lots has been written about him. I'm not sure how much of it is entirely true, or what is simply made up by some of the historians. But we do know this. He was born in Basra, in southern Iraq. He had a rather boring civil service job, sort of a bit like Einstein, working in Bern as a patents clerk. Well, Ibn al-Haytham, unlike Einstein, who spends his spare time dreaming up a theory of relativity, Ibn al-Haytham realizes he wants to do science. He wants to go and study Ptolemy's great texts of astronomy, and he doesn't have time to do that. So in order to get the time to go and study these great works, he feigns madness and gets himself sacked from his job, allowing him time to go off and to do all this great work. Works a treat. He publishes some work. He starts to develop ideas in optics and astronomy. He then hears that there's this new dynasty in Egypt, the Fatimid dynasty, and they've just built their new capital, Cairo. So again, time-wise, we're talking about the late 10th century is when he lived, early 11th century. So 1,000 years ago, pretty much, exactly. And he hears about the Fatimids' problem with controlling the floods of the Nile, for floods and how do you control it for irrigation. He has this great idea. He says, I know what, how about if you build a dam across the Nile, somewhere near modern-day Aswan, by the way, and I'll come and supervise, and I'll. So the caliph, the Fatimid caliph, who by the way is himself known as the Mad Caliph, who apparently ordered all the dogs, stray dogs in Cairo one night to be killed because they kept him awake. And he wouldn't go to sleep until they were all killed together. Anyway, he invites Ibn al-Haytham over to Egypt, and Ibn al-Haytham, it's not clear whether the caliph is with him or whether he goes down to the site where he believes, from studying the maps of Egypt, the best place to build this dam across the Nile is, and he pretty much realizes it's a bigger project than he anticipated. And it's just really, he doesn't know where to start. And so in order to get out of it and not upset the caliph too much, he feigns madness. And that's it, he saves his head. I mean, he basically, it's not clear what he does, in feigning madness. Does he just act like a simpleton, or we don't know. But in any case, he is put under house arrest in Cairo for 10 years, certainly until the caliph dies, after which he's released. But it's during those 10 years that he's most productive scientifically. And he publishes a book on optics. The book of optics, in Arabic, is called Kitab al-Manadhir, which is in many ways as important as Isaac Newton's text on optics, written 700 years later. Ibn al-Haytham was the first person to explain how vision works. The Greeks couldn't understand and couldn't agree on whether we see things because light enters our eyes from the objects, or because we shine light onto them from our eyes, like Superman. Very clever Greeks got this wrong. People like Euclid, the great mathematician, and Plato thought we shone light onto objects. People like Aristotle thought it was light that enters our eyes, but not in terms of rays. People like Euclid, with his geometry, understood he was drawing rudimentary ray diagrams. Aristotle, the great philosopher, thought more in terms of general lightness that surrounds objects, that allows us to see it. Ibn al-Haytham comes along and says, I will use the mathematics of Euclid, ray diagrams, but actually the ideas of Aristotle, because it's light from objects that enters our eyes, and light bounces off them. So he first explains how light travels in straight lines, then he talks about lights to do with incidence and reflection, then he starts studying refraction. And all this goes into his book of optics, which actually ends up being very influential for Renaissance artists in Europe. In particular, his work on perspective. And his text, along with work of other scholars, gets put into a large Latin text called De Perspectiva. And it's the standard book on how, perspective, distant objects being smaller, which is something that artists in the Renaissance were developing. And they based their understanding on the geometry of optics that Ibn al-Haytham had developed. He's famous for, by the way, his Latinized name is al-Hazim. If you've heard of him, you may have heard of that name, al-Hazim, which is the Latinized version of his first name, al-Hasan. A famous problem in optics is one where you have light bouncing off a curved surface, and you want to bounce it off to a particular point. How do you locate the point on the surface? It's much more difficult than just angle of incidence equals angle of reflection, because if that point is ever slightly moved, you've lost it. And to solve the problem requires solving what's called a quartic equation. It's an equation involving x to the power 4. Ibn al-Haytham solved this geometrically, was the first person to do that using what are called conical sections. You take a cone, you can take slices through it at different angles, and it provides a way of breaking up a quartic equation into two quadratic equations and solving where the lines cross. It's what we learn at school as the graphical method. When you want to solve the equation x equals sine x, right? You say y equals x, y equals sine x, and you draw two lines and see where they cross. He developed that method. It was taken on further by another great Persian mathematician, who you will not know as a mathematician, but you will know as a poet, Omar Khayyam. al-Haytham wrote this wonderful poetry that was translated into many European languages. He was actually a better mathematician than he was a poet. I'm not saying he was a bad poet, I'm just saying he was a brilliant mathematician. And he developed Ibn al-Haytham's methods and techniques much further. Okay, one other thing to do with optics I'd like to mention is from a really obscure mathematician in the 10th century called Ibn Sahl. And he wrote a text called On the Burning Instruments. Now, burning instruments, by that they mean lenses, because they mean, you'd have glass spheres filled with water, and how you can, focusing the light into a focal point where you can, create things where I believe is the technique that they're using to light the Olympic torch sometime round about now. Okay? What he does is provide the correct formula for the law of refraction. You see, the Greeks, clever though they were, they had a very approximate way of working out refraction. They said that now we now know it's to do with trigonometry. The sine of the angle of incidence divided by the sine of the angle of refraction is a number. And that number depends on the materials. If light is going from air to water or air to glass, you get a certain number, which is a ratio of refractive indices. So it's the ratio of sines that's a constant. The Greeks thought it was the ratio of the angles themselves. So what they would have said is the ratio, see those chords, the straight lines, horizontal lines that I've drawn, the ratio of those chords within this circle is equivalent to the ratio of the angles. Ibn Sahl was the first person to say that's not quite accurate. That's okay if the angles are really, really small, but actually it's rather approximate if they get large. You really need the ratio of the arcs. Sorry, no, other way around. Of course. Idiot. The Greeks, so ratio of the arcs, right? If you're doing angles and radians. The Greeks said it's the ratio of the arcs that's constant. And he said, no, that's not correct. That's only approximate. You actually need the ratio of the chords, because the ratio of the chords is equivalent to the ratio of sines, very similar to what I explained earlier about the sines. And so he gives the very first and correct formula for what we now call Snell's law of refraction, which came about 6 centuries later. I'm not suggesting we change the name to Ibn Sahl's law of refraction, and who cares what it's called? But here's someone, an unsung hero who's come up with something many centuries before we thought. I'm running out of time. I don't really want to have time to talk much about astronomy. Okay, so I'll very, very quickly say Ptolemy was the great astronomer who synthesized Greek astronomy, and he said that the Earth is at the center and the planets orbit around the Earth, which means they have to have this retrograde motion every now and again because you can't explain things just going around in circles, and it meant he had to have epicycles, circles going around circles. That's the mathematics that was needed in order for Ptolemy to explain what we see out in the sky, if the Earth is at the center. And of course that was all replaced by Copernicus and his heliocentric model. So this is the famous picture in Copernicus's book, The Revolution of Universe, with the sun, Sol at the center, and the Earth, Terra, just one of the other planets. In Arabic science, what did they do in terms of astronomy? Well, of course, they didn't have telescopes. No one had telescopes until Galileo. But also, they were pretty much fixed to the Ptolemaic geocentric view. They also believed that the Earth was at the center of the universe. What they did do was develop a lot of the mathematics that people like Copernicus would later use. An interesting point is whether Copernicus was in fact the first to propose the heliocentric model. Well, actually, the first person, not the Arabic science, the first person was a Greek philosopher by the name of Aristarchus, proposed that it was the Earth that goes around the sun, not the sun around the Earth, and hardly anyone believed him. There was this one, it's quite sweet, isn't it? There's this Babylonian astronomer by the name of Seleucus. You can just imagine, I think you're lovely, I think you're great. Don't listen to them, don't listen, you're right, your theory is correct. He was the only one who followed Aristarchus' heliocentric model. But here's a quote from the great Archimedes. in a book, The Sand Reckoner. He said, you know that most astronomers designate by the word cosmos the sphere whose centre coincides with the centre of the Earth. But Aristarchus, that fool, assumes that the fixed stars and the sun remain stationary while the Earth moves around the sun through the circumference of a circle. Well, of course, that is exactly Copernicus' heliocentric model. So it was around long before him. Indian astronomers have proposed it, and they got, knocked down. There was an Arab astronomer by the name of al-Sijzi who proposed it. Actually, surprisingly, Biruni, remember Biruni is my Da Vinci of the Islamic world, who measures the circumference of the Earth. He didn't quite buy into this heliocentric model, but he has some writing which translates loosely as, it doesn't really matter whether we think of the Earth going around the sun or the sun going around the Earth. It all depends on your point of view. Wow! That's a long time before Einstein. Okay, so there were ideas about heliocentricity long before Copernicus. And just like then, he was courageous in proposing his model, because after all, even Copernicus proposes his model before telescopes. So like then, he was just guessing that was the correct, the way the world is, the universe is. On the other hand, what he did do that no one else really did was turn what was a philosophical idea into a proper mathematical theory that could be tested. And certainly that's what the likes of Kepler and Galileo and Newton would do later. Okay, Galileo, yeah, telescope, blah, blah. I like this picture. I just want to show you this. This is on a frontispiece of a textbook by an astronomer by the name of Johannes Hevelius, so written in 1647. And he's obsessed with the moon. He's studying, this is just after telescope's been invented. So he's using telescope to study the face of the moon. And on the front, he has the two great scientists, astronomers throughout in history, the greatest. He has Galileo with his telescope and Ibn al-Haytham with his geometry and his mathematical calculations. So sort of experimental and theoretical physics appearing on a textbook in 1647. Galileo we all celebrate as one of the greatest scientists who ever lived. But here's another man who is worthy of being up there alongside him. I want to end then with this quote from Ibn al-Haytham, because I'm having bigged him up, I'm going to big him up even more now, and I'll say what he says here is essentially the rudiments of the scientific method as we understand it. We should distinguish the properties of particulars and gather by induction what pertains to the eye to be uniform, unchanging, manifest and not subject to doubt. After which we should ascend in our inquiry and reasoning, gradually and orderly, criticising premises, exercising caution in regard to conclusions, our aim in all that we make subject to inspection and review being to employ justice, not to follow prejudice, and to take care in all that we judge and criticise that we seek the truth and not be swayed by opinion. We tend to regard the scientific method as being laid down by Bacon and Descartes and others in Europe. But essentially that is how we do science today. Ibn al-Haytham was one of those people, even more than any of the Greeks, like Archimedes and so on, who would carry out careful experimental procedures, develop the apparatus, write up the apparatus, write up his experimental method, and alongside that have his ideas, his theories suggesting what he was seeing. He mathematized areas like astronomy, planetary motion, he mathematized optics. And so he was really one of the first true physicists. Now you could say go back to Archimedes and say Archimedes was the first physicist. But Ibn al-Haytham is just one of these greats who somehow seem to have been lost in the mists of time, that it's probably high time we celebrated again. And I should stop there. Thank you very much.